let me ask you, we all think that there's one universe. How could there be more?
Yeah, well, that is the essential question to start with. Because, you know, a long time ago, you know, 2 years ago, the word universe meant just what you are saying. It meant everything, the totality, every star, every galaxy, the whole shebang. So what sense could there possibly be in having more than one everything? Mm-hmm. And what we have found in research that actually dates back a number of decades, but most vigorously relatively recently, is that our mathematical investigations are suggesting that what we have thought to be everything may actually be a tiny part of a much grander cosmos. And that grander cosmos can contain other realms that seem to rightly be called universe, just as our realm has been called universe, which means that you have many universes, multiple universes, which we call the multiverse.
Sounds like a brand of cereal to me, multi-cereal or.
Well, you have a food thing going on here, don't you?
No, don't we? So tell me, I understand that physics is a science, experimental science.
Yes.
So where does this come in? I mean, it sounds more like a religion to me. I mean, there's this universe and another universe. I mean, how do we learn about these other universes?
Yes. So how can you gain confidence in an idea that speaks of realms that we can't see, mm-hmm. that we can't touch, we can't visit, right. we can't observe directly? So let me give the answer in two parts. One is, in some versions of the multiverse, and I should emphasize there's not one proposal for how there might be many universes, there are a number of proposals. In some, there can be subtle connections between the universes that might allow us to have some experimental window onto them. But hold that to the side for the moment. Let's think about the ones where you couldn't visit them. Well, why do we think about these things? Well, we have a belief founded upon really hundreds of years of experience that math can provide a gateway to reality. It can provide a window onto a reality that at the moment the math is being done, we can't actually see or observe that reality. I mean, Einstein is the greatest example, right? He wrote down his equations of the general theory of relativity way back in 1915. Others looked at those equations and found that they seemed to say the universe should be expanding. The math said the universe is expanding. Einstein himself said, no, I don't actually believe that. But 12 years later, observations showed the universe is expanding. The math was confirmed by observations. Other examples are black holes. Again, Einstein's math gives rise to them. Einstein didn't believe it. Observations now show that there are black holes. So we're following in that tradition. We are doing mathematical equations, following them, and as we can discuss in some specific cases, they are leading us root by root to the possibility that ours is only one universe. Does that mean the math is right? We don't know. It has to be confirmed ultimately through some kind of observation or experiment, but the possibility that the math is revealing this new picture of reality is sufficiently compelling that many physicists, including me, are taking it seriously and investigating it vigorously.
But I think the operational word here was can, because mathematics is not physics.
Exactly.
So sometimes the mathematics works, and sometimes it doesn't. You don't have to go very far, but if we go back, you can say the epicycles were invented by a mathematician, a Greek mathematician, and then Ptolemy used them to argue that, you know, the Earth is the center of the solar system or the universe for him. So here's mathematics that's valid as mathematics, not very complicated mathematics, but mathematics nonetheless.
Yes.
That doesn't describe reality. And you can go to later on, for example,
before you leave that example,
sure.
Because I think that is a great example where you had some individuals who were looking at the motion of the Earth and the motion of the planets and coming to certain conclusions that we now know to be erroneous, but conclusions about how things were working. There were other physicists, mathematicians, who looked at that math and said, this is so complicated, this is so convoluted, and if we look at the math this way, it all simplifies, but the conclusion is that the Earth is not the center. So we were propelled by mathematical investigation to imagine the Earth is not the center. And then others, using similar kinds of reasoning, noted that the sun is actually not the center either. And then similar mathematical reasoning showed us that our galaxy is not the center. It's one of many, many galaxies. We've gone through a sequence of, if you will, cosmic demotions. By following the math, confirming it through observation, we may be on the threshold of the next demotion by following exactly the same pattern. Earth is not the center, sun is not the center, galaxy is not the center, our universe may not be the center. It may be one of many universes following exactly the same pattern.
But I think the key is that the mathematics is always simpler in a sense for Occam's razor or something like that.
That's certainly what we have found.
But when you do very complicated mathematics and you trust your equations, often these equations are cumbersome.
I wouldn't say so. I mean, I can understand where you might come to the conclusion because if we get into any of the details, you know, some of the multiverse ideas come from string theory, which seems like a complicated subject when you hear about its features. But when you look at the equations of string theory, the starting point, it's actually pretty simple.
So how many string theories are there?
There's one now. I mean, there was a time when we thought there were a handful of distinct string theories, but wonderfully, in the last decade, the math has come together, and we've realized that what we thought were different theories are actually all the same, just expressed in a slightly different language. So everything has been simplifying. You know, if you take even a good example, Darwinian evolution, the principles of evolution are pretty straightforward, right? But nevertheless, those principles can yield the rich variety of life that we see on Earth. The outcome can be complicated, even though the starting point is simple. That is the way I would characterize our thinking about certain modern physical theories. The outcome, say string theory, again, if we get into it, extra dimensions, vibrating strings, you know, it seems complicated, but that's like the richness of life coming from evolution. The starting point of string theory, like the starting point of evolution, pretty straightforward.
I see. So tell me, what are some of these theories that lead to the multiverse? In your book, you describe several of them. I couldn't find the one with the anti-universe. That's my favorite, actually, where your anti-person, you know, is, you know, positrons and anti, you know,
Watching
protons.
too much Star Trek
Yeah,
or something
right.
there.
So do you favor that route to the multiverse?
Well, there are many ways to the multiverse. Maybe a good place to start would be what I consider the simplest route of all, which is to imagine the possibility that space goes on infinitely far. Right? If you were to get into a rocket ship and head out into the cosmos, would you at some point hit a brick wall? No, most of us don't think that's the case. Would you circle back to your starting point, like what would happen on the Earth's surface if you took a similar journey? That's possible. Or would you simply keep on going forever? We don't know, but let's take that third possibility seriously. If we do, there's a startling conclusion, and it's simply this. In any finite region of space, matter can only arrange itself in finitely many different configurations.
Very
Particles.
large, very large.
Large
but
number,
finite,
but a finite number. Similarly, like if I take a deck of cards.
Sure.
If I shuffle the deck, the order of the cards differ.
Right.
There are only finitely many different orders of the cards. Sure. Many different orders, but still finitely many. So if I shuffle the deck enough times, infinitely many times, the order of the cards has to repeat. Similarly, in infinite space, the order of the particles, the configuration of particles has to repeat too. Now, what would that mean? Well, as we heard in the introduction, it would mean something pretty strange. You see, you and I were just a configuration of particles. Everybody in this room is just a configuration of particles, as is the Earth and the Sun and so forth. If the configuration of particles repeats someplace out there in the cosmos, it means all that we know is repeating.
Yeah,
we are out there. And
right.
that's a very straightforward mathematical conclusion from a simple starting point. Space was on infinitely far.
But you're leaving out an important thing. The measure of that is zero when you go to infinity.
It doesn't matter.
So the probability of us speaking in another universe is, do you want to go there?
Absolutely. In fact, I don't need to frame it in probabilistic terms. Let me just do it in a more concrete setting. If I had that deck of cards, and I shuffled it over and over again, do you agree that sooner or later the order of the cards will repeat? Not the probability. I'm not saying...
The deck is too large.
No, it's 52
really big
cards.
Deck. No,
52
well,
cards.
That's easy. You're taking the easy way out. I'm talking about the universe,
No,
not
but
about
you're discounting the power of infinity.
But
infinite space. This is the supposition. Now, you can challenge that, but let's not, just to get to the end of the argument, if you take on board this idea, which I think most cosmologists and physicists have, that space goes on infinitely far,
No.
then you've got a lot of room for this to happen, and that's the point.
I have a problem with space going infinitely far.
Okay, that's fine. That's a good place to try to poke a hole in this.
In mathematics, dimensions go infinitely far. But in physics, the way I understand physics, these three dimensions in which we live, and the fourth of time, which Einstein taught us, is related to the other three, was created in the Big Bang. So I think if you think as a physicist, and check me if I'm wrong, space here was created in the Big Bang. We're not expanding into another space. We're creating space as we're going out. As the galaxies are expanding with their 13.7 billion years and so on, we are creating three space or four space. So where's the other universe when you're, as a mathematician, okay, there's this dimension, it goes on forever, call it X, and this Y, and this Z. But I think in one of your universes, you've got a universe here, and one here, and one here, and one here, and one here, and infinitely many of them, and that's okay. But does it really exist from a physical point of view when space was really, space and time were created in the Big Bang? So
right. So I do need to correct you a little bit, with all due respect.
That's what I'm here for.
So there is an incorrect image that many people have in mind, which is this. When we think about the Big Bang, typically we imagine that further and further back in time, the entire cosmos was smaller and smaller and smaller. And way back toward the beginning, the universe we sort of intuitively think of as very, very small, and then run that film forward, and as you're saying, space is created from that Big Bang. So how could it ever be infinitely big if it was very small in the past? And if that were the right picture, you would be right. But that was not the picture that's compatible with an infinite universe. In an infinite universe, as you head ever further back in time, the universe is still infinitely big. If you go back in time and the universe is half as large as it is today, half of infinity is still infinity. If you go back further, 1/3 of infinity is still infinity.
But what does infinity mean here?
It's the traditional one, having unbounded.
The universe is infinite?
That's infinitely big, yes.
So what's the radius of 13.7 billion years?
That's the observable universe.
So the universe goes beyond that?
Absolutely.
So what's the Big Bang?
That's
the Big Bang?
That's the key point.
What is the Big Bang?
The Big Bang is an event that gave rise to our realm, but if the universe is infinitely big, then our part, the part that we have access to, is only a piece of the entirety. So you need to make
and the others are expanding as well.
Exactly. So you need to make a distinction between the observable universe and the entirety. The observable universe is just the part that we can see. And you're right, we can't see further back than roughly 13.7 billion light years because that's the amount of distance that light can travel since the beginning. But almost nobody believes that the universe ends at that point. Most everyone believes it goes on at least a far distance beyond that. And the supposition of this particular example that we're saying is that it goes on infinitely far.
Brian, you're a magician too. You pulled out infinity out of the hat, as it were. I mean, what does infinity have to do with anything here? Everything we learn about physics is really finite. What does infinite mean? What cardinality does it have? Does it have the cardinality of the integers or the continuum or the space of functions? I mean, to invoke infinity, you have to give me something.
Yes, and the most straightforward definition would be it's the same cardinality as the real line. It's just the real line extended in exactly the way that you know about from when you took mathematics at a young age. So it just goes on without bounds. So let me ask you this. Let me turn it around.
Okay.
If the universe is not infinitely big, what happens when you travel out?
Well, look, I interviewed Steven Weinberg a few months ago about cosmology, and I asked him, the Big Bang is believed to be a quantum fluctuation. That's what created our universe. What was it a quantum fluctuation in? What was the medium in which we were spawned, if you will? And he said, that we don't know. We can't go there. We don't know. So, but you're telling me something else. You're telling me that there's an infinitude of space. As mathematically, I agree with you. The real line exists, but it exists platonically in a mathematical.
No, I'm asking a very concrete question. If you build a spaceship and you go out and you just keep on going, what happens?
Well, if I take physics the way physics has been done, here's the Big Bang. It started here, but it has location has no meaning. You can't define that point as being located in space because space doesn't exist before the Big Bang from the universe we can see. I don't know about other universes. So if you start here, this space was created with the Big Bang.
So if you go into a rocket ship and you head out into space and you keep on going, what happens?
You can't. You know that you can't. You can't.
What do you mean you can't? You have a ship and you go out.
Well, you can't.
Here are the possibilities. You hit an end.
No.
You cycle back to your starting point. No.
Right. Brian, you know pretty well. If you aim a telescope in this direction at night, and you aim a telescope in that direction at night, the two parts, take the farthest galaxies you can see, they're receding at the speed faster than light because of the accelerating expansion. Well, because of the expansion of the universe, you don't even need acceleration. So that part doesn't talk with this part. How are you ever going to get from one part to another with a spaceship that travels less than the speed of light?
So if you get in that ship, what will happen?
I don't know what will happen. I'd be lost in space.
Right. So it's a mathematical question, which in math language would be, what's the topology? What's the overall topology of space?
Well, that's where I disagree with you. I think topology exists in a mathematician's mind as a Platonic kind of thing, the way varieties or motives or things that may have nothing to do with the real world.
Well, this is
because
a good point.
when you, as a physicist, take parts of mathematics, you actually finessed my key point, which is mathematics is not physics.
Good.
A lot of mathematics here doesn't do anything for us. I'll give you an example.
Yes.
We talked about those epicycles. I'll give you, I'll take your glass, I'll give you another example.
Yeah.
So, fair enough. So how about the other theories? Tell us about some of
the other ways that you can get to multiverse theories.
Right.
Well, another simple one is one that comes out of thinking very carefully about the Big Bang. So again, we touched on the Big Bang earlier, which is this idea that the universe underwent this rapid expansion early on. But one of the things that perhaps we don't emphasize enough when talking in general context is that the Big Bang theory actually leaves out something pretty important, which is the bang. The Big Bang Theory tells us how the universe evolved from a split second after whatever started the outward swelling to happen in the first place, but it doesn't tell us what caused that swelling to actually occur. Now, people have been working very hard to fill in this gap, and the reason I bring this particular gap up is because there is a proposal now for what caused the outward swelling. It's called inflationary cosmology. It's basically the recognition that goes back to Einstein that gravity under certain circumstances can be repulsive. We're used to gravity being attractive. You drop the glass, it falls because the earth attracts it. You drop the ball, it falls, again, because the earth pulls things together. That's what gravity does. But actually, Einstein showed, surprisingly, that under exotic circumstances, gravity can actually push things apart. The belief is that, the possibility is that in the early universe, that exotic environment was realized. There was an energy suffusing space that gave rise to repulsive gravity that pushed everything apart. That's why the universe started swelling in the first place. The thing is, when you study this theory in detail, it seems to show that this outward swelling would not have been a unique one-time event. It says that there could be many of these Big Bang-like beginnings at various and distinct locations in a much larger cosmos, each giving rise to a swelling realm, each giving rise to an observable universe, and a universe that people like us could inhabit, but there could be universes upon universes upon universe. This is the inflationary multiverse. And the nice thing about this approach is that the idea that space underwent this rapid swelling early on from this repulsive gravity, that has been subjected to some very interesting observational tests. If the universe went through this rapid swelling early on, here's what would happen. Little tiny quantum jitters, quantum fluctuations in the young universe would be stretched out by the rapid swelling and smeared out across the sky. An analogy is if I had a little balloon with a fine-tip pen. Imagine I wrote a little message on the surface of the balloon. You couldn't actually see it, it's too small. If I blow air into the balloon, as the balloon stretches, my message gets smeared out across the surface of the balloon. Now you can see it. Now the tiny quantum jitters in the early universe may behave similarly. They're like the little message. And as space underwent this rapid expansion, that message gets smeared out across the sky as tiny temperature differences in the heat left over from the Big Bang. It's called the cosmic microwave background radiation. And we have measured this heat left over from the Big Bang, and the way the temperature varies from point to point is exactly in line with the mathematical calculations.
But
and that is a very convincing piece of evidence for at least taking this theory quite seriously.
I think the theory is taken very seriously by most, not only cosmologists, but even astronomers and, and physicists.
Yeah.
The question is, does it really imply the existence of something that's unobservable as of now, which is a multiverse? I think that those microwave fluctuations, and as they expand, and I think there are galaxies that are spawned from them as well. And,
sure.
Does that really imply, other than the mathematics, you keep going back to the mathematics, doesn't mathematics really tell you that if you see this picture of the microwave background radiation in space, you must have a multiverse?
No.
Okay.
Not must. And that's why I'm not here saying that these ideas are proven. You may recall when we started out this conversation, I emphasized that these are speculative ideas that come from our investigations. And until we have observation of them, we can't believe that it's real.
Let me ask you,
but
let me
just take it a little bit further. But what happens in the subject is when you have a theory that is able to describe things that you can see, it bolsters your confidence to follow the theory further. That's where the confidence comes from, to follow the math further. Now, does the math uniquely imply that there have to be these other realms? No. There are versions of the inflationary theory where there'd only be one realm. They're very hard to come by. They're very cumbersome. They feel very contrived from a mathematical standpoint. That doesn't mean they're wrong. They could be right. But the ones that don't have that contrived quality are the ones that do give rise to these other universes. So do we know that they're there? Absolutely not. But does this suggest this as a compelling possibility that's worthy of further study? Yes. And how would you know it? What sort of experiment might give you some insight? Well, here's, again, rhetorical. So if you had these... if you had these expanding realms...
I'll shut up if you want me to.
Not at all. If you have these expanding realms, imagine it, as a big cosmic bubble bath of different universes, with our universe being one of those bubbles. Now, in a bubble bath, the bubbles can collide. Similarly, these universes, as they expand, can collide too. If they form close enough together, they can smash into each other. How would we know that if our universe had a kind of fender bender with another universe in the past? Well, that collision can send ripples through this heat left over from the Big Bang, this cosmic microwave background radiation once again. So scientists are looking in that background radiation to try to find finer patterns in the temperature variations in space that might indicate that we got hit by another universe. Is there any positive evidence yet? No, not yet. The collisions could yield a signature that's too small for our current level of technology to access, or maybe it never happened. But that's the way in which, in principle, you could have observational evidence of a universe that you can't literally see. You see its effect in our universe.
Can I speak now?
So please.
So how would you know? There have been several generations of satellites looking at the microwave background radiation. Yeah. And we know a lot about the microwave background radiation. In fact, it's uniform to 1 in 10 to the 6 or something like that. The fluctuation is very, very small.
Right.
How would you be able to tell? I mean, you've got to give us something concrete. If you say, here's a universe, and here's another universe, and they collide. You know you lost me at the beginning, because I don't think another universe can exist on this axis. It just because of the fact that we created this space. What is this space? You haven't answered my question on that, but let's leave that out. So hold on, let me finish. So you crash these
But you're giving the impression that there's something missing, and the missing part is actually you're not fully comprehending the idea, because we're talking about in very general terms.
I know what you're thinking. Yeah. There's the hyperspace there, and the
hyperspace.
Calabi-Yau manifold, and we're...
Knowledge can be a dangerous thing. You sort of know too much right now.
I would apply it to you, Brian.
This has nothing to do with hyperspace, nothing to do with extra dimensions. Bread and butter cosmology that takes place in the ordinary dimensions have this possibility. So let me just describe it. So the wider cosmos that you're having trouble grasping, think of it as a big sauna, a steam
It's in
bath.
R3. It's in three-dimensional.
R3, yes, 3 dimensions. Let's just stay simple. So 3 dimensions that's filled with this dark energy that causes the outward repulsive gravity that I was referring to. What happens is, region by region in this big cosmos, the energy can degrade. And as the energy degrades, holes open up in this wider cosmos where the energy turns into particles that make stars and galaxies. So our universe is simply one of these regions where the energy has degraded. The inflaton energy has degraded. The image that works pretty well is, think of a block of Swiss cheese. Imagine that the cheesy part of the Swiss cheese is where this energy exists and is forcing things to experience gravitational repulsion. The holes in the cheese are places where the energy has degraded, where stars and galaxies can form. So the different universes that I'm talking about are just the different holes in this big expanding block of Swiss cheese.
So they're really one universe.
Whatever language you'd like.
Fine.
Again, as I said early on,
let
me just say, as I said early on, the language is confusing.
Fine. Let's leave it at.
Yeah.
Let me ask you. We're talking about experimentally detecting the